We started with the intuition of a linear classifier using the sentiment analysis example. Let's take a little bit of a next level dive and understand more about what a linear classifier model really captures. In particular, we're going to take some data set, some training data set, which is going to feed us x's. We're going to get features out of that, just like we did in the regression course, and we're going to feed that to the machine learning model for classification, which is going to output the predictions y hat. And that model depends on some parameters w hat, which we're going to train from data. Now let's go back to that example that we had with just two features with non-zero coefficients, awesome and awful. Let's suppose that we had a third feature with non-zero coefficient. Let's say that the word great. Now in this case, every data point is associated with a coordinate in this three-dimensional space. So for example, this data point over here might have 5 awesomes. It might have 3 awfuls, and it might have 2 greats associated with it. And what a linear classifier model is going to do is try to build a hyperplane that tries to separate the positives from the negative examples. And the hyperplane is associated with the score function. And the score function is going to be a weighted combination or of this coefficients W0 multiplied by the features that we have. So W0 plus W1 times number of awesomes, which in our case was 5, plus W2 times the number of awfuls, which in our case is 3. And finally, W3 times number of greats, which in our case was 2. So for this data point over here, the score of xi is going to be defined by W0 plus 5 W1 plus 3 W2 plus 2 W3. And if this, depending on the coefficients, that score might be positive or negative. Since this is a positive training example, we'd want to choose the W's that make that score positive. Now that we set up the classification problem and the task that we're after, let's do a quick review of notation for the course. In this course, we're going to use the same notation that we used in the regression course. That was the second course in the specialization. And here we had an output y, which is the thing we're trying to predict. In the regression case, that was a real value, but in our case is a class. And we have a set of inputs x, which have little d dimensions, x1, x2 through xd. So x is really a d-dimensional vector, and y is an output we're trying to predict, which in our case is either -1 or +1 in the binary classification setting, which is where we're starting out today. Now, we'll use xj to denote the jth input, which is kind of a scalar value. We're going to use hj of x to denote the jth feature. And then we'll use x sub I, very importantly, to denote the ith data point. And x sub I of j to denote the jth input of the ith data point. It's a little bit of a handful, but it's exactly the same as what we did in the regression course. Now, with this, empowered by this notation, we can go back and define our simple hyperplane, the one we just saw with awfuls and awesomes, and just say that in this case, y hat, our prediction, is the sign of the score that we have for this particular input. And the sign function just says that if the score is greater than 0, predict +1, and the score is less than 0, predict -1. And then at 0, you have the choice of either predicting -1 or +1. You can make an arbitrary choice. The way I think about it is, if it's 0, I predict +1. Now the score of an input xi is W0 plus W1 times x1 of I, then plus W2 times x2 of I, all the way to WD, the dth coefficient, times the df entry in the xi vector. And here, the features input, the first one is 1, is a constant feature like we did with regression, and x1 could be awesome, number of awesomes, x2 could be number of awefuls, and say the last one, xd, could be the number of times the word ramen shows up, which to me might be associated with a negative review, but it might be kind of indifferent. Depends on what coefficient you have there. So our goal is to optimize the score, fit the score, and I'm going to use W transpose xi as a shorthand, so I don't have to always write W0 plus Wi x1 plus W2 x2 and so on. So we use this transpose notation, which is the same one that we talked about in the regression course.